Hello everyone, I am Ashin. Today I am going to talk about voltage stability and how to measure it. Let's see the instrument. I'll use this GW Instec GDS3652A. There is a built-in power analysis function.
Maybe you have experience about building a PC. We need a power supply.
Its job is simple. It provides a stable DC power to main board. It just provides a voltage, right? Anything special?
Actually, it is not so easy to get a stable voltage.
To control a switching power supply, understanding complex mathematics and control theory is needed. To make it simple, I don't go deeper for the complex theory. I will focus on the basic concept and skill of the stability measurement. Why does stability matters for the main board? Because the main board experiences significant fluctuations in current. When we listen to MP3, the PC just consumes a small current for playing music. At the next second,
we may try to convert HD video format.
At this moment, the computer draws a significant amount of electrical current. At the same time, the voltage will drop a little bit. Now the power supply should be able to provide more current to do compensation. It makes the voltage return to the level it's supposed to be. This process is called voltage regulation. To get stable voltage, or we say regulation, we need a control loop in the power circuit. Let's see a circuit.
This is a demo board of a USB charger.
It comes from TI. I am going to use it to do an experiment. Let me introduce it.
Transformer is a separator. Primary side we have 110 volts input. Right side is secondary, which has 5 volts output.
If the right side voltage is greater than 5 volts, the feedback network effectively plays a significant role in reducing the period of conduction current on the primary side of the system. If the output voltage is less than 5 volts, the feedback network increases the period of conduction current on the primary side. After several adjustment periods, the output voltage will stabilize at 5 volts.
This is the original idea of negative feedback stabilization, and it sounds a great control method.
But it is a bit different in practice. When the voltage tries to return the original level, damped oscillation may happen. The shorter period of the damped oscillation, the better stability we have. The longer oscillation time or even continuous oscillation means the poor stability. Therefore, it's important for us to take into account the stability of the power supply during the design phase. Now we use gain and phase margin concepts to measure a power supply system stability accurately. Wow, what's that? Recall our microelectronics subject. This is a negative feedback system. Let's say its transfer function in S-domain looks like this. If we try to make the system stable, we must avoid the situation where the open loop gain, beta A, equals -1. Otherwise, the denominator becomes 0. In this way, the gain of the loop is infinite. It makes system divergence. The voltage will be unstable, so when we design a power supply, it is not allowed to make the beta A equals -1 in operation frequency range. The minus sign and number 1 can't coexist. So stability is evaluated by how far is it from the -1. Or we say how far the system will fall into the pothole. To measure the stability, assume this is beta A's curve in S-domain. When the angle of it reaches -180 degrees, we measure the distance starting from -1. The distance that we are referring to is commonly known as the gain margin. On the other hand, when the gain of the curve is just 1 unit, or we say 0 decibels, we measure the angle starting from -180 degrees. The angle is referred to as phase margin. Anyway, these methods are used to evaluate the beta A curve. They can help us ensure that beta A curve and -1 are not too close.
Now we are going to measure the gain margin and phase margin of this demo board.
I will show you the method to measure the stability. We focus on the voltage feedback loop. We put a low resistor in series here. This demo board has been installed this low resistor here. Then we put a transformer in parallel here. Now we feed the external AC signal. So we call this particular transformer an injection transformer for AC signal input. The input signal we have here is floating. So the voltage difference across the low resistor may fluctuate over time. So, We can observe the system response by injecting external signal while the system is running. This low resistor is the cut point for observing the open-loop response. The TP3 is the input which is closed to feedback network. In this case, TP2 is the output closely aligned with Vout. We connect the oscilloscopes CH1 and CH2 to the input and output individually. Don't use probe to hook up with original ground lead, since the SMPS generates a large magnetic field, which makes the probe induce interference voltage like this. So I use two RG316 cables to extend TP2 and TP3 from the SMPS. Then connect to the oscilloscope here. The oscilloscope's ground lead needs to be replaced. The probe ground lead needs to be replaced by the spring tip. By using spring tip, we obtain a minimum loop area and achieve the lowest noise. We must connect with the injection transformer in this situation. Here it is. I winded it by myself. Of course, there are ready-made ones in the market. Here I use the homemade transformer for a simple measurement. The whole test environment looks like this. This is the test result. The noise seems a little bit smaller, but though it can be better. I try to take the signal generator's ground point, which is near the transformer, and then connect it to the ground of oscilloscope's probe. It seems the noise has been suppressed more. Now I think we can start the measurement. We observe the frequency response between V-in and V-out. We mainly observe the curve of gain and phase along the frequency axis. This oscilloscope can draw Bode plot. Then we can evaluate the distance between the open-loop gain and the point -1. There is the power analysis option in this oscilloscope. It includes the control loop response function. The instrument has a built-in signal generator. It handles transmitting and receiving signal by itself, so it can measure the frequency response. Let's enter the menu. Signal amplitude. Let's see the signal amplitude. The signal amplitude is set to 200 mV. Because the transformer will be saturated when the voltage is high. Saturation also occurs with low frequency. After several tries, I discovered the appropriate level is 200 mV/Vpp. Let's turn on the DUT power. Press Run button. Now we have to be patient, since it takes some time. I am going to speed up the video. When the process comes to an end, the display clearly shows the beta-A Bode plot. The blue trace is gain, the red one is phase. To improve the red trace, I have to turn on the unwrap function. After tuning on the unwrap function, the visual effects on the phase trace will appear more continuous and seamless. Now we press Analyze. Measure. Press Cursor. After some computation, you will see the oscilloscope displaying the gain margin and phase margin. Gain margin is the gain while the phase is at 0 degree. Here is the 0 degree of the phase. The gain is about 8.2 decibels at 0 degree phase. Let's talk about phase margin. Let's consider what the corresponding angle would be when the gain is specifically set at 0 decibels. Let's take a look. See, this point here is 60 degree. Now some of you may have a question. You mentioned the reference angle -180 degree. Why is it 0 now? That is because the open loop that I previously referred to is cut right at the negative terminal of the adder circuit. So apparently the open loop gain is just beta-A. When implemented in real-life scenarios, the cutting point can only be at Vout. There is no other choice. So the open loop includes the adder's negative terminal. Open loop gain becomes negative beta-A. The V-in here is DC there, which has no AC component. We don't consider V-in in open loop. Just imagine V-in as 0. Consequently, the original open loop gain beta-A changes and becomes minus beta-A. The additional negative sign means the transfer function has been rotated 180 degree. So the unstable point currently at -1 will eventually move to +1. The gain margin doesn't change. In technical terms, phase margin becomes the definition of the quantity of angles from 0 degrees. Actually, it becomes more convenient for observing. and doesn't impact the analysis. We usually ensure that the phase margin we design is greater than 45 degrees. Then, the gain margin should not be equal to 0 decibels. You can set it to 5 decibels, 10 decibels. I think all of them are acceptable. It depends on your design. You can see here is a glitch at the end of the trace. This is the switching frequency of the power transistor in this SMPS. When the injection signal frequency is close to this switching frequency, or even beyond this frequency, the measurement we have read then somehow becomes less meaningful. Because the injection frequency is too fast, the transistor can't switch in time. Basically, we are primarily concerned only with the front portion of the trace. Today I made an introduction for oscilloscope GDS3652A. The power analysis option includes a control loop response function for efficiency. I hope that you have learned something new today. Don't forget subscribe Strong PyLab. Goodbye.